Okay, this is Jack Jackson. We're back with our third of our series of lectures on quadratic functions. And let's start by reviewing some stuff that we did in our previous lectures. We have quadratic functions have three good forms. The general form is p of x equals ax squared plus bx plus c, where a, b, and c are constants. And from this form we can easily see the y-intercept, so you might call this the y-intercept form, because you can easily see that 0, c is the y-intercept. The standard form is p of x equals a times parentheses x minus h close parentheses square plus k. And this could easily be called the vertex form as well, because we see that hk is the vertex. The factored form is p of x equals a times x minus root 1 times x minus root 2, and this can be called the root form because you can see the roots r1 and r2. It could also be called the x-intercept form if it has x-intercepts, because if r1 and r2 are real numbers, then r1, 0 and r2, 0 are the x-intercepts. However, if it doesn't have x-intercepts, r1 and r2 will turn out to be non-real complex numbers. We have some easy ways to convert among these. If you have the standard form or the factored form, just use FOIL and distributive property and combining like terms to turn it back in the general form. If you have the general form or the factored form, it's pretty easy to get the standard form. We have completed the square and used that in the past to come up with some nice formulas. And we have this nice formula. If you have the a and the b, you can do h equals minus b over 2a to get h. So if you got the general form, this tells you h from the standard form. On the other hand, if you have the factored form and you want to find h, you just average the two roots, r1 plus r2 divided by 2. Either way, you get h, and then you just take h and plug it in place of x in the form that you started with and solve that, and that will tell you what k is. So k is just p of h. Now you have h and k, so you got the standard form. If you got the, if you want to find the roots, well, if you've got the factored form, you've got the roots. The standard form is pretty easy. You just plug 0 in place of p, subtract k, divide by a, take the square root, remember plus or minus, and add h, and you got it. Pretty straightforward solving equations. But if you got the general form and you want to go forward to the factored form, you either have to complete the square, or since we've completed the square in general, we can use the quadratic function to find r1 and r2. r1 is h plus the square root of d over 2a, and r2 is h minus the square root of d over 2a. Or one of them's r1 and one's r2. Doesn't really matter which is which. So, remember, h is minus b over 2a, and d is b squared minus 4ac, and so that is the quadratic formula. Notice that the a is the same a in all three cases, and if a is positive, then we've got concave up, so it opens up, and if a is negative, it's concave down, so it opens down. Okay, so we can see that. So here's one. We looked at this one before. Notice that it is from the x squared minus 8x plus 7. You can see this y-intercept there. From the last version, you can see at 1 and 7 on the x-axis. This distance between the h and here is 3, so it's 4 plus, so the square root of d over 2a is 3. And so the roots are 4 plus 3 and 4 minus 3. And so you can actually see each part of that quadratic formula visibly on the graph. And of course your vertex is down at the bottom there. Okay? So what are our basic conclusions? Every quadratic function is simply a transformation of the standard power function y equals x squared. So all the shapes have the same basic, graphs have the same basic shape, like the one above called the parabola. We have very nice formulas for the vertex and y-intercepts of the graph and the x-intercept. We can use these to solve any quadratic equation. We can use these as a guaranteed method of factoring any quadratic trinomial into two linear factors as long as we're allowing complex coefficients. We have three forms. Each tells us something very interesting about it, and we can even these formulas and techniques that we have for going from one to the next are pretty straightforward, so we could actually even put these into a calculator if we wanted to. Let's look at the meaning of the discriminant. The discriminant d has about 4 different cases. That's the b squared minus 4ac. If d is 0, then it turns out that r1, r2, and h are all identical, and the version of the equation that we have here is both the factored version and the vertex version. So it's both the standard form and the factored form. And since x minus h shows up as a factor twice, it's called a root of multiplicity 2. And what that happens is the vertex is on the x-axis. That way, if a is positive and if a is negative, it's this way. But it crosses there at h. h0. If d is non-zero but a perfect square, then when you take the square root of d, it comes out to be an integer, and so your roots are rational numbers, and it crosses the x-axis twice at root 1 and root 2. One of them's on the left, one's on the right there, and the axis could be anywhere, say over here. And so those roots are rational numbers. If d is a positive number but not a perfect square, same way it looks that way again, or it could look this way, where it crosses the axis at 2 different places. But these are not rational numbers. They could be irrational numbers. So back in beginning algebra, we would said that would be a prime polynomial or irreducible, or we said it wouldn't factor. But it does factor if we allow, and it does not factor if we only allow integer coefficients. But if we allow irrational coefficients, it does factor. But if d is a negative number, then it will not factor even with real coefficients, but it will factor if we allow non-real coefficients, and so the graph is either all above or all below the x-axis, and it doesn't even touch the x-axis at all. And so when you're taking the square root of negative, you're going to end up with an imaginary number I in there, because remember the square root of negative 1 is going to give you I. So this does give us a guaranteed method of factoring polynomials, quadratic polynomials. So let's look at solving some equations and factoring using the quadratic formula. So if we have x squared plus 4x minus 5 equals 0, that is ax squared plus bx plus c equals 0, we just write down the quadratic formula there, substitute in here. Okay, everywhere there's an a, put whatever a is, which is 1 in this case, and then b is 4 and c is negative 5, and just plug in and simplify. In this case, notice that we got the square root of 36, which was 6. 6 over 2 is 3. So negative 2 plus 3 is 1, and negative 2 minus 3 is negative 5. So the roots are nice. Not only are they rational, they're actually integers here. And so that means it factors as x plus 5 times x minus 1 times the coefficient of 1, which we can leave out because it's just 1. Well, this one we could have factored it the trial and error method, and it might have been even easier to do. So either way, it factors this. We can see it factored out. Over here on the one on the right, we would never be able to factor this with trial and error because it doesn't factor with integer coefficients. We end up, most of this is the same as the one on the left as you work it out, but we do get a square root of 6 here. So it factors, but only if you allow coefficients. Also this is coefficient 1 in the beginning, so still a 1 here. And it's just x minus, put the root in parentheses, x minus, put the other root in parentheses. Okay? So 2 roots. There we go. A couple other examples. Here's another one. So, why is that my way? I don't know. Alright, here we go. Got it out of the way now. 2x squared plus 6x minus 5 equals 0. Plug in. So minus b over 2a minus 6 over 2 times 2. 2's cancel here, leave a negative 3 halves. So there's your h. B squared is 6 squared, so that's 36. Minus 4 times a times c, that works out to be 40. That's 76. Notice 76, we factor it as 2 squared times 19. So we can reduce that radical to 2 times square root of 19 if we want to need an exact answer. The 2 and the 4 cancel down to a half there. And so we get negative 3 halves plus square root of 19 over 2, which is approximately 0.679 something. And we also get the other one, which is negative 3 halves minus the square root of 19 over 2, which is negative 3.679 something. So there it factors. Don't forget that we need this leading coefficient. When we have this leading coefficient here, we have to have it down here as well. So don't, when you get so worked up finding the roots, don't forget that you need that there as well. Alright, so here's an example. Those were a couple examples where we had irrational roots. So to factor it, we had to use the quadratic formula. Here's one we don't have to use the quadratic formula, but it's a lot easier than factoring it with trial and error on part D. So I've got some pretty big numbers here, but just plug them in. I do this either by hand or with a calculator to help me out. And it finally comes down to a reduced fraction here, which is actually this is a terminating decimal, and a reduced fraction here, which is this is a repeating decimal. So that means it factors right here as 896 times x minus 81 over 16 times x plus 15 over 56. I really like that version of the factoring better because it has the roots right there. 81 over 16 and negative 15 over 56. But I can also take 896 and break it apart as 16 times 56. So again, I prefer this factored version. But now if I take the 16 times here and distribute, and the 56 over here and distribute, I get it factored this way, which is the way you would have factored it back in Algebra 1, where you had to do common anti-foil, trial and error, guess and check, however you want to call that kind of factoring. However, there are 384 possibilities for that trial and error that you would have to check. If you're a particularly bad guesser, you could have to try 384 things before you finally came across the correct answer. Of course, if you're a good guesser, you might come across it more easily. So here, this illustrates that even though you could have done this with the trial and error method, it's much easier to do this one with the quadratic formula. Whereas up here on this one, probably it's easier to do the trial and error method than it is the quadratic formula. Take your pick. Either one works. So whichever one works for you. Sometimes the quadratic formula is the only way to do it, like this one here. Notice this one, when I work this down here, I've got a square root of a negative, so that's going to turn out to have an I in my answer. And of course, when I graph this one, it's not going to cross the x-axis. Here's one where I have decimals in it, and I'm not going to try to find an exact answer. Actually, that may actually be an exact answer right there, but I'm going to go ahead and get a decimal approximation there. And so my factoring is going to be approximate down here. And here you see some exercise. So throughout these notes you have exercises, and what you should do is do these for practice, and the models are right there, just right above that. Okay, so these here are equations for solving. So you solve these equations, get it equal to 0. If it's not equal to 0 already, get it in that form, and then you can apply the quadratic formula. Or perhaps you can do it by just factoring with trial and error factoring, whichever works for you. Got your choice. These down here boils down to the same thing, but this time you have to factor it. You might be able to see how to factor it right away. Okay? Or you might have to use the quadratic formula to come up with factors. So finding the roots, finding the factors, really boils down to the same thing. So I'll tell you what, let's let you practice those. When you think you've got that down, come back and then watch the next video.